This is just reviewing a little bit about the rules of exponents, particularly if you have some base with an exponent that's a fraction. Essentially what you're doing is you're taking the root of that number to the power of the numerator. So like we said, a to the 1/2 power is the square root of a, or a to the 1/3 power is the cube root of a. So if you have a to a fraction, you take the root of the denominator essentially to the power of the numerator. Here are some examples. So 16 to the 3/4, you take the 4th root of 16 and then you cube it. Well, the 4th root of 16 is 2, 2 cubed is 8. If you have, like this one, 27 to the negative 1/3, remember that negative exponent means you have to move it to the denominator. The 1/3 means it's a cube root, so it's 1 over the cube root of 27, which is 1/3. Same thing here with 64 to the negative 1/2. The negative means you take the reciprocal, and you have 64 to the 1/2 power. So that's 1 over the square root of 64, which is 1/8. This slide actually goes along with part in your textbook that talks about the types of numbers that an exponent can be if you have a function that is, for example, 2 to the power of x. If your domain is simply the set of integers, then you end up with these points. But we don't have to only use integers. We can use rational numbers, which include fractional values. So now the points get closer and closer and closer and closer together. And then the last one shows, well, really, I don't need just rational numbers. I can use any real number as my domain. It gives me a nice smooth curve on my graph. Here's showing some properties of exponents. First of all, they're saying that your base has to be positive, and also it cannot equal 1. So as long as x is a real number, you can take any number to that power. Two powers are only equal if their bases are equal and their exponents are equal. If your base is greater than 1 and your m is less than n, then essentially a to the m power would be less than a to the n power. The reason they tell you this is because of the contrast here. If you're dealing with fractions, then the smaller exponent will lead to a larger value. If you look at what's written down here, which is also in your notes, it tells you that properties A and B require that A is greater than 0 so that it's always defined. And what they're showing you here is negative 6 to the power of x is not real, because if you put something like x to the 1/2, that would be like taking the square root of negative 6, which is not a real number. So that means that a to the x power will need to be positive. Because of that, it says if you look at property A cannot equal 1 because it says 1 to any power is equal to 1, right? 1 times itself, however many times you want to do that, is always 1. So if you look at property B, it can't equal 1 because here if we have 1 to the 4th and 1 to the 5th, they're equal, but 4 and 5 are not equal. So these are just some rules that you should be aware of. I'm not going to ask you to repeat them back to me. Now we're going to take a look at some problems. We are given the expression f of x is equal to 4 to the power of x. So we want f of negative 2. That means we're looking at 4 to the power of negative 2. Remember, I told you a negative exponent means you need a reciprocal. So that's 1 over 4 squared, which gives you 1/16. In the next one, we're looking for f of 5, so that means I'm looking for 4 to the power of 5. Well, that's simple enough to put into my calculator. 4 to the power of 5 is 1,024. The next one's where it gets a little bit trickier. We're looking for f of 2/3, which means 4 to the power of 2/3. So we can do this in a couple of ways. The way that I would approach this is I would say 4 squared to the 1/3 power. 4 squared is 16 to the 1/3 power. And then I'll be looking for the cube root of 16. Now when I solve something like this, I know some things about the number 16. For example, I know the prime factorization of 16 is this. And I also know that if there are 3 2's under this radical, because the index is 3, I need 3 2's, I can pull those 3 2's out and get 2 times the cube root of 2. The last problem, f of 2.15, it is a real number, so I can raise 4 to that power. Again, this is something that I would put into my calculator, and when I do, I get 19.698, and that's an approximation, it's a rounded value. Exponential functions are what we've just seen. It's some f of x is equal to some number to the power of x. Means it's the function with a base a. And remember, 1 cannot be the base of a, because if it is, then you end up with just whatever value you put in for x, the answer is y, and it's a constant function at 1. Here's what we're looking at when we're talking about graphs of exponential functions. The domain here is from negative infinity to infinity, meaning you can put any number you want in for x. The range, if you look at this, is from 0 to infinity because it's never negative. Okay, it's going to get really close to 0, but it'll never be negative. This function is always increasing, and it's continuous. There are no holes. There are no vertical asymptotes anywhere on this function. The x-axis is the horizontal asymptote, and it tells you as x approaches negative infinity, that means the asymptote is going in this direction. Some other things that are important are the points that it passes through. First of all, it always passes through 0, 1, because any number to the 0 power is equal to 1. So this number will always be on the graph. It's going to pass through the point 1a, because any number to the first power is exactly that value. And then it's also going to pass through negative 1, 1 over a, because if you have any number to the negative 1 power, it's just the reciprocal. That's contrasted with this function. This is the function f of x is equal to 1/2 to the power of x. Again, domain, negative infinity to positive infinity. I can put any number I want in for x. The range is 0 to infinity. Again, we've got this asymptote here, but it does go up to infinity. This function is fractional, right? We can't have any negative values. We can't let it be 1, but it can be between 0 and 1, meaning it can be a fraction. It's always decreasing, and again, it's continuous, meaning no horizontal or no vertical asymptotes, no holes in the graph. Again, the x-axis is the horizontal asymptote as we approach positive infinity, meaning as it goes in this direction. But notice the graph actually goes through the exact same points. It's still going to go through 0, 1. It's going to go through the point 1a right here, and it's going to go through the point negative 1, 1 over a. So whether you're dealing with a base number that's greater than 1, or a base that is fractional, it's still going to pass through those 3 points. A few more generalizations on this graph. It says if we start with 2 to the power of x and we replace x with negative x, what ends up happening is you get 2 to the negative x, which is essentially negative 1 times x. 2 to the negative 1 is 1/2. So this is why these two graphs actually reflect across the y-axis. This is the general shape of these kind of graphs, where a is greater than 1. anytime the A value here, this number here, gets larger, your graph just gets a little bit steeper. But the shape is about the same. When you have a fractional value, again, this is essentially the shape of the graph. So there's really only two shapes. This picture actually shows several functions graphed on the same coordinate plane. Pay attention, they all go through the point 0, 1. You notice this blue one here has a base of 2, the red one has a base of 3, the green one has a base of 10. So it just rises more steeply. Looking at the reciprocals, 1/2 is in blue, 1/3 is in green, 1/3 is in red, 1/10 is in green. And then again, these characteristics are going to be the same. The points that are always on the graph, if A is greater than 1, you've got an increasing function. If it's a fraction, it's decreasing. The x-axis is the horizontal asymptote. You can put in any number for domain, and the range will go from 0 to infinity. When I need to graph these, I'm actually not going to plot a whole bunch of points. What are the points that I know have to be on this graph? Well, if x is 0, y is 1. Always the case. If x is 1, y is 1/2. And if x is -1, y is 2. So, general shape of my graph. So 0, 1 is here. 1, 1/2 is here. -1, 2 is here. And then what I do is I sort of just sketch it. I am not looking for a perfect graph by any means. Now taking a look at this next problem, hopefully you're going to say, wait a minute, you cannot have a negative base. And you would be correct. However, one thing that we can do, because it doesn't say -3 to the power of x like this, because that we could not have. So the way that we approach this problem is we will think of this as -1 times 3 to the power of x. That we can do. So the first thing that I will do is I know that when x is 0, y is 1. When x is 1, y is 3. When x is -1, y is 1/3. But I need to multiply every single one of these by -1. So really, when x is 0, y is -1. When x is 1, y is -3. And when x is -1, y is -1/3. There's 0, -1. 1, -3 is here. -1, -1/3 is here. This graph is going to do something along these lines. And that will be your graph. The domain is from -infinity to +infinity. The range is from -infinity to 0, meaning that it's going to continue forever negatively, but it's not going to approach the x-axis in this direction. This next one's a little bit interesting because it's 3 to the x minus 2 power. Well, again, I can start with what I know. I know when x is 0, y is 1. When x is 1, y is 3. When x is -1, y is 1/3. And I actually might start by plotting those points. But then I actually need x minus 2 to be the number that I'm actually looking for. Well, the way I think of this is kind of like when we did trig, remember, and we were translating those sine waves left and right, and minus meant go to the right and plus meant go to the left. Same kind of thing is happening here with the minus and plus. So this -2 means we're actually going to move to the right 2 units. So this point here is going to move over 2 units to here. This one will move over 2 units as well. And then this point will move over 2 units. So that the graph kind of looks like this. Now let me show you why that works. By the way, it should not touch the x-axis. If you put in 2 for x, you'll get 2 minus 2, which is 0, and 3 to the 0 is 1. So at 2, we're still up here at 1. If you put 3 in for x, 3 minus 2 is 1, and 3 to the 1 is 3. And then if you put 1 in for x, you get 1 minus 2 is negative 1, so you have 1/3, which is about right there. So that's why that works, but again, I think of this kind of like just shift it over to the side. The domain of this function, we can put in all values. The range, again, we're going from 0 to infinity. Once again, different kind of problem, looks a little different. Hopefully you know what this constant is going to do to the graph. By this point in the year, I would expect that. But again, because it's exponential, we'll start if x is 0, we know y is 1. If x is 1, we know y is 3. If x is negative 1, we know y is 1/3. Those are the things I'm always going to check first with an exponential function. So 0, 1 is here, 1, 3 is here, negative 1, 1/3 is there. Now, this minus 2 right here, that's going to start changing these numbers. And subtracting 2 means we move everything down 2 units. So that the graph looks like this. Remember, anytime you add or subtract a constant, it's going to move your graph up for adding, down for subtracting. So let's talk domain and range. You can still put any number in for x, so your domain is negative infinity to infinity. For the range, now we actually are crossing the x-axis, but hopefully we're starting to recognize that there is an asymptote right here at negative 2. So the range goes from negative 2 to infinity. Our last set of problems looks at solving equations where your variable is actually in the exponent. There are algebraic ways to do this that we're going to learn later in the chapter, but for now there are some that you should be able to rationalize. So we'll take a look at this first one. 5 to the x is equal to 1 over 125. Well, first thing that I need to pay attention to is that this is a whole number, this is a fraction. That tells me that x has to be negative. So that's sort of the first place that I start, is I'm looking for 5 to be to some negative number. Then I think about, okay, well, what do I know about 125? Well, 5 cubed is 125. So this one is actually one of those ones that's a little bit ridiculously simple to rationalize. That 5 to the negative 3 power is going to be the same as 1 over 5 cubed, which is the same as 1 over 125. So in this case, x is equal to negative 3. The next one might not be quite as simple to see. So we have 3 to the x plus 1 is equal to 9 to the x minus 3. What I want to do is I want to rewrite this so that it's got a base of 3. That's sort of my big goal here. So I'm going to keep the 3 to the x plus 1, but I'm going to change 9 so that it's 3 squared to the x minus 3. Now, you remember how I made you learn all those power rules? This is why. Anytime you take the power of a power, you just multiply your exponents. So the 3 to the x plus 1 will stay the same, but on the right side we end up with 3 to the 2x minus 6. Now, one of those things that I made you learn at the beginning of this section is that if we have two bases that are the same, that are equal, then that means these exponents have to be equal, which makes this problem a lot simpler because it means that x plus 1 has to equal 2x minus 6. So solving here, I will bring x over and get just x on the right-hand side. And I will add 6 to both sides and get 7. So in this case, x is equal to 7. For this last problem, my variable is not in the exponent, but it still requires a little bit of maneuvering in order to solve this. So I have b to the 5/2 power is equal to 243. When I rewrite this, I am going to rewrite this as the square root of b to the 5th power is equal to 243. So now to undo all of this, the first thing I want to do is take the 5th root of both sides. So that I have square root of b here. Now you might be thinking, how on earth did you know that you could take the 5th root of this number? Well, the way that I knew that is I took the prime factorization of 243, and I got that it was 3 to the 5th power. So the 5th root of 243 is simply 3. Then I'll square both sides and find that b is equal to 9.